Hey, good afternoon, everyone.
Good afternoon.
All right, so exam one, I graded those, and I don't know, did I get those done yesterday? Sorry, I had done part of them the day of the exam, and then it got real late, so had to finish up yesterday evening. So sorry for those of you who had to wait a little bit. Here are the grades. The orange shows the grades for exam two. The blue shows exam one, so you can kind of see for each student, like whether or not the grade went up or down. We had 9 students grades go up. We had 14 students grades go down. The class average on this test was a 79. Compare that to exam one, the class average was an 83.5. So it went down. It went down by about 3 or 4 points, the average, which is to be expected.
There was also one less bonus question.
Yeah, that's true. Right. We also had, we have a smaller standard deviation, which is good. It just means that more students are kind of clumped together. The number of A's, B's, C's, D's, and F's didn't change too much. We had more C's, but similar number of A's, similar number of students who didn't pass. So, overall, I thought it went good. I mean, in grading it, I thought it went real good. There's a couple of problems where I kind of got you a little bit. And I'm going to go over those real quick because I think there's like 1 or 2 problems that only maybe 3 or 4 students got. So I'd like to discuss those. Otherwise, I mean, I guess I would just be concerned, if you have 2 grades now that are not passing, you're going to want to maybe talk to me about, how we proceed from here. And I'll leave the ball in your court for that. Just reach out to me, come to my office hours, call me, text me. We can have a conversation. So as far as the exam is concerned, let's see here. So in the exam, I think the problem that was tricky, this one got quite a few people. The graph of the derivative, the left side of the graph, the slope of the tangent line, you could say is 0 or really, really small and positive, then it gets really big positive. But on this side, the slope of the tangent line is always negative. So your graph's got to be below the x-axis here. But that's not the one that was tricky. I think the one, okay, number 7, this one got a lot of people right here. This one right there. Because I'm wanting you to find the values where this function f has a tangent line that's parallel to this line. And to be parallel to that line means that the slope of the tangent line and the line, see, you have to recognize y equals 6x minus 4 is a line, right? You have to, y equals mx plus b, you have to realize that. And then you have to say, oh, well, I need the slope of the tangent line to be parallel to the slope, to that slope of that line. And the slope of this line is 6, right? The m, the number in front of x, is the slope. So that means you want to know when the derivative of this, not this, but the derivative of that in green, when is that equal to 6? And when you do that, you get a quadratic equation, which you can solve. I saw all sorts of things. I saw people take the derivative of this and set it equal to this, 6x minus 4. I saw people take derivative of this, set it equal to 6x. Close, but it's just the slope that has to match. I also saw people take derivative of this and set it equal to 0, which means you're finding where the slope of the tangent line is horizontal. So that's not what we want. So this problem was not on the review, but it was in your homework. So I wanted to make sure that I put something in here that was in your homework problems, something similar to a homework problem. And then the last one was one that got people. So let me just go to the last one here. So you're supposed to find the equation of the normal line. So what you're going to do is first just find the slope of the tangent line and then do the negative reciprocal of that slope and use that for the slope of your normal line. But you have to successfully take the derivative of this. And I think what a lot of people missed is that there's a product right there. So you have to do a product rule on this, which I do here. And then you have to take derivative of tangent x, which you need to know from class or from your formula sheet. The derivative of tangent of x is secant squared x. And I gave you a hint because you need to take that secant squared x and evaluate it, plug the x value 0 into it. So you got to know what secant squared of 0 is. And so you have to know that secant is 1 over cosine. So you're just really trying to figure out what 1 over cosine of 0 is, and then square it. And cosine of 0 is 1. So this comes out to 1. Plug in 0 into this. You should get 2 here. That's the slope of the tangent line. Then you take the opposite reciprocal and you get -1/2. And then you use your point slope formula. I know I'm going through that fast, but I want you to at least see what I was looking for. I think those 2 problems were the most inconsistent with the review, I guess. You know, it's like there wasn't something exactly like that on the review. I think everything else, for the most part, followed the review pretty closely, unless you disagree. I think the algebra on this first one was easier than what was on the review, and the algebra on this one was very similar to what was on the review. Any questions, comments, concerns? Okay.
No, sir. After the test, I called Ethan.
Yeah.
We went over the entire test, and that's when I started noticing all those little details on this.
Yeah.
And it was right after. I was like, damn it.
Yeah, I know, man. I mean, like, I know some of y'all put a lot of time and effort into getting ready for that test. So I'm always rooting for you all to do well. You know, so when I see little things, I'm like, you know, it's like you're there, you're almost there, but then little things, then they start to add up, and you know, the A becomes a B. So it's, yeah. But you know, what's
I
that?
just glanced at mine, and number 5, I lost a point on that one for a real dumb reason on my part.
Yeah.
I just forgot to
Yeah.
do the last step entirely.
Yeah, plug in 1.
Yep, didn't do that.
Yeah. Yeah. So I mean, y'all know from class, I mean, I make mistakes too when I'm sitting here doing stuff, right? So I understand. It's the problem is you'll get someone who takes tests and they don't make any mistakes, right? So they'll deserve the highest grade, and so I have to take points off, right? So, all right, we proceed. So today's a real important day. We are going to be finishing up. We had started the section on product rule and quotient rule. You were only tested on product rule because that's all we covered, but we never got to the quotient rule, right? So now we want to talk about the quotient rule. So the quotient rule, what's that?
Is this 2.4?
I think it is still 2.4. Yeah, I'm pretty sure. Let me just double check. Yep, 2.4, product and quotient rule. So after today, you should be able to finish up this homework assignment. In fact, probably focusing on all the stuff in green here. All right, so just a recap of the major things we know. Okay, I just want to recap because we took a test, and you know, so we know first of all the power rule, right? Which basically says if you take x to the n, you take its derivative, you've got n x to the n minus 1. We know that if we have a sum or a difference, right, we have a way of doing this. So if you take 2 functions, f and g, add or subtract them together, it doesn't matter how you do it, take the derivative, then we can do each one separately. I hope this notation makes sense. It's just to kind of recap the rules, right? Take 2 functions, add or subtract them, take the derivative, well, just do them individually. So we're always happy when we see pluses and minuses between things. We had, what else? The product rule, right? The product rule allows us to take care of a derivative if we have a product between 2 functions. So if we have f times g, right, then the derivative of this, unfortunately, was not clean. It was this formula. All right, that's the way I taught it, right? You take derivative of the first one times the second plus the derivative of the second times the first. Okay, so that's where we are right now. I mean, there's other things. We know the derivative of sine is cosine, derivative of cosine is negative sine, all that. We have the other things too, but this is like kind of just a recap of the formulas we've learned. So now we talk about the quotient rule. And the quotient rule basically establishes how we can take a derivative when we have a quotient, a fraction. So if you have some function f on top of some function g being divided, and you want the derivative, then the formula for this is pretty ugly looking. It is f prime times g minus g prime times f. Now, when you look at that, I'm not done, but when you look at this part of the formula, do you all see that this formula is basically the product rule formula with a subtraction in between instead of an addition? Right? Otherwise it's the same formula. But there's one more thing you have to do. You have to take the entire numerator there and divide it by g squared. Now, when I say g squared, I don't mean take the derivative of g, just take g, whatever the bottom is, and square it. All right. So that's the rule. I'm not proving it, right? I won't do the proof for this. The only one here that I've proved is the power rule. I proved that, and I had to use Pascal's triangle and all this stuff. And so we kind of waved our hands at the proofs for all these, but we're going to take this one on faith. And let's just do an example. Let's just get right into it. So let's take the test problem. The test problem. Yeah, let's do that one. The problem number 2 was to find the derivative at a of this function, x minus 3 over 2x plus 1, right? So f of x equals x minus 3 over 2x minus 1 plus 1. I already forgot. What was it?
-1.
Was it minus 1? Okay, so this is it. So we want the derivative of this, right? So the way I'm going to look at this is as if I have a quotient, right? Does everyone see you could kind of act like this numerator is like an f, even though this is called f, I'm just going to kind of ignore that right now. I'm going to say that's kind of like an f, and then this is kind of like a g. So I have f over g, right? So if I want to know what the derivative of this is, what I'm going to do is I'm going to take the derivative of the top one, right? Which is f. I'm going to take derivative of that. So let me write that down. I'm going to take x minus 3. I'm going to take its derivative. Then I'm going to multiply that times g, which is the denominator, but not taking the derivative. Subtract from that the derivative of g. So now I take the denominator, 2x minus 1. I need to take its derivative. And then multiply that times f, which is the numerator. Notice how I'm using parentheses here? Because when we multiply this all together, we need to make sure that whatever this is gets multiplied times this whole thing. I saw a couple of issues in the exam. I'll go back and show you in a minute what I'm talking about. Let's finish this one out. But I'm not just throwing parentheses here for fun. I mean, it's important in terms of the algebraic manipulation when we simplify this. All of this divided by the bottom, which is 2x minus 1, that's g squared. And now I just take the derivatives, okay? The only derivatives I need to worry about are here and here. That's the only pieces of this that I need to do calculus on. So I need to take derivative x minus 3. There's a minus sign between them, right? So I can do them individually. The derivative of x is 1, and the derivative of 3 is 0. So I should just get a 1 from there. And I still have times 2x minus 1. Minus. Now I take derivative of what's in here. Take derivative of 2x, I get 2, right? Take derivative of 1, I get 0. So 2 minus nothing is 2. And then I still have times the x minus 3. And then all of this over the bottom squared. I don't do anything to that. And then I'll just do some algebra here. There's not a whole lot to do. I distribute a 1 through here, so I get 2x minus 1. I distribute a negative 2 through there. I get negative 2x plus, no, hold on. Yeah, plus 6. All right. Over 2x minus 1 squared. Y'all see what happens up top?
Yep, 2x's go away.
1 take away 6,
Yep. 5.
5 over the bottom, which is 2x minus 1 squared. I think I might have written the problem down wrong. Hold on. What was the exam problem? I thought it was, see, it was plus 1. Y'all told me it was minus 1.
Oh, I'm sorry. See, that's where my mistakes come from. Okay. I look at
Okay,
them
it was,
once.
it
I'm
was
like,
plus
okay.
1 here. We're not going to get the same answer. Oh, well. What we did is correct, but it's not the problem from the test because I put minus 1. Do y'all see what I'm saying? It's here. Let me go back. Okay, so this is the answer. We're done. Now, just because I want to see what it would look like with the test problem. If we do it and we change this now, let's correct this. This is a plus 1. How does that change things? This becomes a plus 1. This becomes a plus 1. This becomes a plus 1. Okay, so that's all that changes here. Here, I have a plus 1. When I take the derivative of this, does it change? What's derivative of 2x plus 1?
Should just be 2 still.
Still 2, right? And then on the bottom, I have plus 1 here.
Yeah.
This is what changes when I distribute. So when I distribute here to here, I get 2x. And then here to here, I get plus 1. And when I distribute here to here, I get negative 2x. And then plus 6. And when you add up these, the 2x's cancel, you just get 7 over 2x minus 1 squared. That matches what you should have got on the test. So the basic idea, right? The basic idea of the quotient rule is that it's basically the product rule formula with a subtraction, right? And then just divide by g squared and you're done.
Doesn't seem too bad.
Okay, yeah.
Seems like you'll probably end up with a little nicer answers than with the product rule because of that subtraction. Potentially more stuff will cancel out.
We might get more things to cancel, yeah. So I'm going to show you something now. I mean, we're going to do more examples. Okay, so don't freak out. We're going to do more. But I want to show you our formula sheet. Okay, and let me erase some stuff here. Let me copy this. This is our formula sheet and what they have written for the quotient rule and the product rule. All right. So that's what's on your formula sheet. That's what the textbook has. So what I'm going to do is below this, I'm going to rewrite it kind of using a different notation. Instead of this, I'm going to say F times G. And then they're taking the derivative. That's what this means, right? Take the derivative. So I'm just using the prime mark instead. They're saying this is F times the derivative of G. See how they do that? F times the derivative of G, and then plus, then they do G times the derivative of F. That's the book's formula, right? What I told you is this, F times G derivative. I said, this is F prime times G plus G prime times F, right? That's the way I taught it. This is the way the book uses it.
Yeah.
Now, first of all, these are the same thing, right?
Yeah.
Because when you have multiplication between two things, you can flip the order, right? That's called the commutative property of multiplication. 2 times 3 is 3 times 2. So if I flip these over, right, then I get G prime F. If I flip this over, I get F prime G, right? And then addition is also commutative, right? 3 plus 4 is 4 plus 3. So if I rearrange those, then I get my formula, right? That I presented to you. Yes. I'm going to try and show you why I do it, okay? So now over here, let's see what the book does. The book says this is F over G, and we're going to take a derivative, right? Take the derivative. And they say that this should be G times, that's G times the derivative of F minus, then they say F times the derivative of G, and then all of that over G squared. That's the book's version. I say f over g, take the derivative, and it should be f prime times g minus g prime times f all over g squared. So that's the way I teach it, right? This does not match exactly here. It looks different, right? These look different, these look different. They're the same thing, but they look different, don't they? I just trying to explain to you all why I do it this way. Because when you go to the formula sheet, you're like, it doesn't match what he showed. And if you go to a tutor is probably going to show you this way and this way. That's probably the way they're going to do it because that's the way they learned it. Can anyone speculate as to why I teach it this way?
It's just easier to remember, similar to the product rule versus the other one, like just it looks a little different, so it's more likely to mess it up.
Yeah, exactly. So when I was a student, I learned these two rules, right? Just like you were learning them. And I was taught this rule, so I memorized it, right? FG prime plus GF prime. And then the quotient rule comes along and it looks completely different. It's GF prime instead of FG prime, right? It's GF prime minus FG prime. So that it's like all different, right? Like this formula looks so much different than the product rule. To me, it did, right? But if we just use like algebraic properties, you can move things around and you can rearrange them to make them look very similar. And if you do that, then you really only have to remember the product rule. And when you get to quotient rule, you throw in the minus and divide by g squared and you're done. So it's really less to have to put up here. That's why I did it. So I just want you to know that. You go get help or you're talking to a friend who's in a Cal 1 class somewhere else, and it looks like y'all have two different formulas. There's a reason why, okay? Just want y'all to understand that, okay? Any questions on that at all? All right.
Questions from me?
All right, so let's do some more examples. Do y'all remember me saying that when you're learning the product rule, like instead of trying to memorize like f prime g plus g prime f, to think of it more like the derivative of the first one times the second plus the derivative of the second times the first. That to me is more useful, to think of it more generally like that. If you can do that for the product rule, you have a similar way of doing it for the quotient rule. You say it's the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. All right, derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared.
With the quotient rule, there's actually one that it really matters where it is with that denominator.
Yeah, it matters the denominator, and you can't rearrange the order of these, right? You
Yeah,
cannot
because subtraction is not commutative.
It's not commutative, so you cannot flip those. But it's okay, as long as you follow this form, you're good.
Yeah.
All right, here we go. Let's do another one. How about this? We'll keep it nice for now. So how about we do sine x? Oh, probably should put like y equals sine x over x squared plus 1. I want us to find y prime. So what's the derivative? So I realize I have a quotient, right? I look at the top, I look at the bottom. I can almost treat this like a little f and a little g, and then I can just apply my formula. So my derivative will be the derivative of the top times the bottom. Oh, I forgot to show you all that thing. Minus the derivative of the bottom times the top all over the bottom denominator squared. The only two derivatives I have to take are these two right there. So the derivative of sine is cosine. So we get cosine x, and then in parentheses still x squared plus 1. Then minus, now we need the derivative of x squared plus 1, which is just 2x, and then times sine x. The entire thing divided by x squared plus 1, that quantity squared. Now, our derivatives are going to start to look pretty ugly, and we're not going to spend a lot of time trying to simplify these or clean them up. I think this one right here is fine if you just left that as an answer. You could also, if you want, distribute the cosine through. If you did that, you would get x squared in front of cosine x plus another cosine x, then minus 2x sine x. The whole thing over the x squared plus 1 squared. You with me?
I think I got it.
Okay.
So if we left it like on the top, would that be fine as like, you know, what you call it, the raw derivative or something?
Yeah, it's kind of like the raw derivative. So what we're going to be doing eventually, if you go back and think about the very beginning of this class, the whole idea was, can we, if we are given a function, no matter what it is, can we find the highest and lowest points on the graph? To find the highest point means you need to figure out where the tangent line is 0. To figure out where the tangent line is 0 means you need to figure out where the derivative is 0, which means we're going to have to be setting these things equal to 0. So we will be solving this equation right here that I have in this box. We will be asking ourselves when that's 0. And we'll have to solve that equation. Now, when we do that, we're going to be forced to do algebra. We'll have no choice. For now, let's just make sure we understand the mechanics of getting the derivative. Then we can go suffer through the solving the equation part. That'll come later. Not that far later. It is coming, but it's still a bit away. Okay, you good? All right, let me do one. Let me do another one. How about this? Find equation tangent line at 0, 0. All right, so I'm given a curve, right? And we want to know the equation of the tangent line at that point 0, 0. Let's go take a look at the graph. Just curious to see what it looks like. We have x sine x over x squared plus 1. That's going to be a boring answer, but there it is. There's the graph of the function. And we're going to go to the point 0, 0 and find the equation of the tangent line. It looks like it's going to be flat, right? So I'm thinking the equation of this tangent line is just going to be y equals 0. But let's keep going, all right? All right, first thing we need is the derivative, right? We need to figure out what the derivative of this is. So do y'all see the difference between this problem and the one before?
Yep, we have multiplication on the top. So we have to
Yeah, we
use
got to
our,
do the product rule.
So we have a quotient, right? We have a quotient here where the numerator is actually a product, right? And the denominator is not a product. It's just the sum of two things. So we actually have a problem where we have a quotient, and within the quotient, we have a product. Understand? So I'm going to look at it first like the entire numerator is f, and then the entire denominator is the g. And I'm going to use the quotient rule. The quotient rule says that the derivative of that should be whatever the top is, take its derivative, and then times the bottom, do not take its derivative, minus now the derivative of the bottom, then times the top. All of that over the bottom squared. Understand? Derivative of the top times the bottom, minus derivative of the bottom times the top, all over the bottom g squared. So if you compare that to what we had up here, it's very similar, right? The big difference is this. This right here Here we took the derivative of sine x, right? Here we're taking the derivative of what?
X sine X.
X sine x, right?
X times sine X.
Yeah, that's x times sine x. So when you take the derivative of that, you now have to apply the product rule to that piece. To that piece, you have to apply a product rule. So that's going to be a little bit complicated. Let me see. I need to take this top left derivative. So I'm going to give myself some space. Everything I do in blue is going to be the derivative of this piece. So I have to do the derivative of the first one times the second one plus the derivative of the second one times the first one. Do you all see how this in blue represents the product rule being applied to x sine x? Now, next to it, we still have x squared plus 1, and then minus. Now, this derivative I should be able to take. That's not a tough derivative. I hope I can say that right now. 2x is derivative here, and then we still have times x sine x. All of this over the x squared plus 1 squared. I still have two derivatives to take right here, so I'm not done yet. So I'm now going to work on this derivative and this derivative here. Those all live within that parenthesis, right? So derivative of x is 1. So 1 times sine x is just sine x. Plus, when I take derivative here, I get cosine x, right? And then I'm going to multiply it times x.
X
So
cosine X.
Yeah, save myself a little time. I'm just going to put the x in front of the cosine x just so it looks better. So I don't accidentally put those x's together. I still have the x squared plus 1. I still have the minus. Now this I can put together. I can put those x's together as x squareds, as an x squared. And then I take the whole thing and put it over that square. At this point, we've done all the derivatives, right? Like there's no more like calculus to do. Everything from here on out would be algebra. So I think I'm happy with that as an answer. You could, if you want, multiply these together by, foiling. You'd have to go here to here, here to here, here to here, here to there, and then subtract that other piece. You'd have a big old ugly long numerator. I'm not going to though. All right, I'm just going to leave it. Is that all right with you?
Sounds good to me.
There's no, so this is our derivative, right? I mean, we're not done though. Remember, we wanted the equation of the tangent line, right? So if I want to find y prime at the point we're talking about, x was 0 there, right? I need the derivative at x is 0. So now what I'm going to do is plug 0 into this. Everywhere I see x, replace with 0. So I have sine of 0 plus 0 cosine 0 times 0 squared plus 1 minus 2 times 0 squared times sine of 0. All of that over 0 squared plus 1 squared. Sine of 0, God, this little gnat's been bothering me since like 8:30 this morning. Okay, sine of 0 is 0.
Yeah.
Plus 0 times, who cares? Cosine of 0 is 1, but who cares? Because we're multiplying times 0. So this whole thing right here, everything is 0. And then this right here is a 1. Right? And 0 times 1 is 0. So I get top left corner is 0. Minus 2 times 0 times sine 0. That's all 0 also. And then over 0 squared plus 1 is 1. So we get 1 squared on the bottom. This comes out to be 0 over 1, and that is 0.
Slope 0, so we have a
Slope
flat
of
line.
Flat line, which is what the picture indicated would happen, right? So, but I still need the equation, right? Still need the equation. So now I go back to the good old point slope formula. Y minus y1 equals m times x minus x1. The point we're talking about is the point 0, 0, right? That was given in the beginning of the problem. And the slope we just found was 0, right? That's our slope.
How is
Pardon?
all of that first term of the numerator 0?
For this right here,
Yeah.
sine of 0 is 0, right? The y coordinate at the angle 0.
Wouldn't that? Okay, that makes sense.
Right. So at an angle of 0, your y coordinate is 0. Yes? So sine of 0 is 0. 0 times who cares, right? This is going to be 0, but just for the sake of knowing, cosine of 0 is 1. So 0 times 1, that's still giving me 0. So I'm adding two zeros together, it gives me 0. Okay, back to this. So I'm going to just go y minus 0 equals 0 times x minus 0. A bunch of zeros in here. The left side is y. The right side doesn't matter because the slope is 0, right? Y is 0. So that's the equation of the line. And if you have an equation of a line, y equals a constant, it's a horizontal line, right? So when I go graph this, if I graph y equals 0, I get the x-axis, right? Which is tangent to this curve at that point. All right, you ready for some more? Ready or not? Here it comes. All right, this one I'm gonna let you work on for a little while. How about this? How about x plus x cosine x over x squared sine x. I'm gonna put you in breakout rooms.
You're a mean person.
I'm not mean. Not mean. Okay, I want to see if y'all together in groups can figure out, there's a lot of little things happening here, the order in which you do things. Talk to each other. I'll give you about, I don't know, 8 minutes, see what you do. Breakout rooms, here we go. Be about 3 or 4 of you in each room. There you go. Find the derivative. Sorry, I just want you to find the derivative. You don't need to do anything else. Find y prime. Right, I know I didn't give you a whole lot of time. How did that go, though?
I mean, I got it right, but like I barely finished by the time came up, and yeah, like we were still
yeah.
finishing. We really didn't have a chance to discuss it.
What I really was hoping is that everyone would get at least this first line, where you're just, okay, I'm applying the quotient rule, right? So here's my top function, here's my bottom function. I don't care what they are at this point. Whatever the top is, whatever the bottom is, the bottom is. The quotient rule says I need to take derivative of this one, so that's this, derivative of it, times the bottom one, subtract from that the derivative of the bottom, so I still have to take that derivative, times the top function over the bottom squared. So is that first step clear to everybody? It's okay?
Yes.
Now, the next thing you have to do is you actually have to take two derivatives, right? The one in yellow and the one in green. Now, when you do the one in yellow, now this is like your new little universe, okay? All you're doing is thinking about this right now. If you had to take the derivative of that, how would you do it? So if you need to do this and go to the side and write down x plus cosine x and try and take this derivative by itself, then do it on the side, okay? And now you have addition between two terms, right? So you can do these individually. You know that the derivative of x is 1, hopefully, right? And then you say plus, and then you say, oh, crap, I've got a product here, right? I've got a product between these two. So I've got to do a little product rule here, right? So that's what I've written down here. The derivative of this will be the derivative of x, which is 1, plus now the product rule on this. So it's the derivative of this one times this one, plus the derivative of this one times this one. I still will have to go take those derivatives, but at least I have that written down. That's all in this first parenthesis, right? That's all. It's very important that all of this is in its own parenthesis here. And then you still have this x squared sine x, you still have the minus. Then you have to take derivative of this one. So again, maybe you need to come over here to the side and be like, okay, what's the derivative of this? Product rule there, and then do your little product rule. I did it all in one, on one page, so, or in one line. So I took the derivative of this times this plus derivative of the sine times the x squared. Put that all in parentheses because again, it's this part, and then the rest of it, and then over the g squared. So does that second line make sense? Good?
Yeah.
Now I have 4 derivatives I have to take, right? I have to do this derivative, that derivative, that derivative, and that derivative. And now I finally have gotten it down to a point where those derivatives are pretty clean, right? There's no product rule, no quotient rule left. It's just, replace this derivative of x is 1, right? So 1 times cosine x is cosine x. This, I kind of did it, but I cleaned it up in my head. The derivative of cosine of x is negative sine x, right? So this derivative would have given me negative sine x times x. I still have the times x. And what I did is just move the x in front there and then change this plus to a minus. That's what I've got here. And then on this one, I rewrite everything, right? And then on this one, I take derivative of x squared, which is 2x times sine x, plus the derivative of sine x is cosine x. We don't have a negative that pops out. So I just put the x squared in front of that cosine. And then this right here, and then all over the bottom squared, and this right here is our very ugly raw derivative. Okay. So remember a few classes ago when I said, we finally get to do away with the limit, right? We're going to do away with the limit. We're going to get these shortcut rules, and you're going to be happy, and then you're not going to be happy because the functions will become more complicated. As you can see, now that we have the rules, we can really start to take derivatives of some pretty interesting looking functions, right?
Yeah, imagine having to do that with a limit.
Oh yeah. Yeah, with the limit, that would be horrific. Probably
That's when
not
you change your major.
That's why we have rules, right? Because they help us, right? They help us. All right, so I mean, that's the rule. mean, there's nothing more to it, right? It's just now you have to start practicing with this rule. And yeah, all right, so let's see here. Yeah, you're not gonna like this. If f of x equals x cosine x, find the 28th derivative of that. Now, this is not necessarily a quotient rule problem, all right? I'm working a problem from within the same section that's similar to one of your homework problems. We have to take the 28th derivative, which makes me think we're actually not going to take 28 derivatives. We're probably going to take derivatives and look for a pattern, right? So let's see if we can start this. Let's take the first derivative of this. So when I take the first derivative, I have a product, don't I? I have a product rule right there. So I have to do derivative of this one times this plus derivative of this times this. So can someone tell me what the first derivative will be?
Negative x sine x.
Okay. Is that it?
Which should be cosine x minus sine x, right? I mean, cosine x
Cosine
minus
x.
x sine x.
Minus
Yeah,
x
cosine
sine
x minus x.
All right,
So
so
it's like
how do we do
the-
this? Derivative of x is 1, right? Let me do it. I'm gonna do the first one. Okay. It should be the derivative of x times cosine x plus the derivative of cosine x times x. That's our product rule, right? Not quotient rule, that's our product rule. Derivative of x is 1, so 1 times cosine x is cosine x. Derivative of cosine x is negative sine x times x still. So this should be cosine x. I'll move the x out into the front here, minus x sine x. That's our first derivative. Right?
We're just gonna lose the additional x's after a couple of these.
I don't think the x's are ever going to go away. Yeah, because you're going to constantly have product rules. Let's
Oh,
do
yeah, I think I see.
let's do the next derivative. So any questions on that first derivative? Okay, the second derivative is, all right, well, look, I have subtraction, don't I? So I can do them individually. So I first take the derivative of cosine of x, which is negative sine x. All right, that's just a derivative of this one. And then I have minus. Now this is really important. Watch what I'm about to do. I have minus, right? This is a product. And so I must apply the product rule. And when you apply the product rule, you're going to do like derivative first times second plus derivative second times the first, right? You're going to have two things when you do the product rule. So I'm going to put a bracket here. You could use a parenthesis right after that minus sign. This minus is this. And now I do the product rule on this, which is the derivative of x times sine x plus the derivative of sine x times x. With me? Equals negative sine x minus, still here, derivative of x is 1, so I just get sine x. Derivative of sine x is cosine x, so this will be cosine x times x, so I'll write it this way, x cosine x. Questions there?
Can we simplify that down a little?
I'm going to simplify right now. Negative sine x minus sine x minus x cosine x. I distributed the negative through. See, if you don't put this bracket or parenthesis, it's going to be all messed up. This negative must pass through both terms. But when I pass it, now those first two terms can go together as negative 2 sine x minus x cosine x. And now I have my second derivative. All right, so while we're doing this, on the side here, I'm gonna start listing out what we've got here. When we do the zeroth derivative, right? The zeroth derivative was the original function. When we did the first derivative, we got cosine x minus x sine x. I'm referring to that right there. When we did our second derivative, we got -2 sine x minus x cosine x. And that's where we are, right? That's where we are. Okay, let's keep going. We got to go until we find a pattern or until we get to the 28th derivative. I hope we find a pattern. Okay, the third derivative. All right, so now, okay, I have subtraction between these two, so I can do them separately. On the first one, I do not need a product rule because -2 is a constant. Constants come for the ride. So the -2 will come down and then the sine of x, take its derivative and get cosine x. So I should just have -2 cosine x for that. Are we happy with that?
If we did try and apply the product rule to that first one instead of doing the constant thing, would it just be the same thing?
It would work, but you would open yourself for
Just be longer?
mistakes. It would be longer and there's more potential to make mistakes. But yes, you should get the same answer. Look, I'll do it over here. If you were to look at -2 times sine x, and if you wanted to do the product rule, you could. It would be the derivative of -2 times sine x plus the derivative of sine x times -2. And when you do this derivative right there, you get 0. So that's 0, right? Derivative of constant 0 times sine x. And then over here, plus derivative of sine x is cosine x times -2. So your final answer is -2 cosine x, which is the same thing that I got, right? But I highly do not recommend this. Okay, because it really, not only does it take more time and give you more chance for error, it really demonstrates to everyone around you that you don't understand how constants act with functions. Does that make sense? I mean, it's just like yeah, okay. But if you do it, you're not, you could get it right still. All right, here we go. All right, so now I've taken the negative down here, right? So I'm just looking at this guy right here. I need to take its derivative, which is a product, right? So I've got to go derivative of x times cosine plus derivative of cosine x times x and figure out what that is. So we have -2 cosine x minus bracket cosine x. That's because derivative of x is 1. So just cosine x. And then here, derivative of cosine x is negative sine x. And then times x. So I'm going to put negative x sine x. Distribute the negative. I can put the first two together. Okay, there's where we are now. It's our third derivative. This is a good problem just because it forces you to like repeatedly do product rule and keep track of signs, and it's just a good exercise, which is why I'm showing it to you. All right, so now the third derivative is -3 cosine x plus x sine x. Do we see any patterns yet?
I mean, our sines and cosines are following the pattern that they have before when we've done problems like this. It also
Yeah.
looks like our the constant at the beginning is counting upward, but they're negatives. I'm gonna bet the
Yeah.
next one's gonna be a +4.
Yeah, so we have a couple of things that we might see as patterns right now. We might. It just depends. Like you could look at that as being a 1 in front of the cosine x. And then, so like what distinguishes the two terms? These terms have an X in front with the trig function. These are just a trig function, right? With a number in front. So it's like 1 in front of cosine, -2 in front of sine, -3 in front of cosine. Maybe we can predict what the next one will be. It probably has a 4 in it, right? And maybe, what do you think, sine or cosine?
That should be sine.
It looks like it's switching. right?
Four
Cosine,
sine
cosine,
x.
sine. 4, maybe -4, I don't know. We need to do another derivative to really see it. And then over here, it was x sine x, now it's x cosine x, the next sine x, maybe the next one's x cosine x. This was minus, minus, this is plus, maybe the next one will be plus, maybe it'll be minus, I don't know. I think we need more, don't you agree? We need more to really establish this pattern. So I'm gonna do a fourth derivative. I'm gonna squeeze it in right here. So this was remember where our third derivative was, our fourth derivative, right? Which I'm gonna start doing it this way. Our fourth derivative is the derivative of this right here. I'm gonna use this, I'm just gonna look at this one. I'm gonna try and go a little faster here. I can do these separately. -3 times cosine x, the -3 comes for the ride, right? So I've got my -3 there. Times, now the derivative of cosine is negative sine. That takes care of the derivative of this piece. Now I say plus, oh good, I don't have to worry about distributing a plus through, but I'm still gonna put a bracket because what goes here is the derivative of this, right? That's a product rule. My product is right there. So I'm just curious how fast I can do this. If I can start showing less, I don't know how y'all are gonna feel about this. I'm gonna try and do this one mentally. The derivative of the first one is 1 times the second one plus the derivative of the second one, which is cosine x times x. There's my little product rule on that second piece.
You can also look back to your second derivative. You had to do that on one of them. So you can just.
That's right. That's right. If you look at the beginning, well, in this piece right here, when we took the derivative to get the second derivative, this came out, right? We've done this already. Okay, let me clean this up. This is going to be, when you put these two together, right? Multiplying them, the negative and negative multiply to be positive sine x. And then here, I don't need to worry about distributing negative, so I'm going to have plus another sine x. And then at the end, I'll have plus x cosine x. And then put the first two together, I get 4 sine x plus x cosine x. So that's where we are now, 4 sine x plus x cosine x. And this is our fourth derivative.
I think we can identify a pattern now.
You think we have enough for the pattern?
Well, we have because our trig function should be looping now effectively. They'll just start looping.
So what do you think the next one will be then? Tell me what you think the next one will be, and then we'll check it.
5 cosine x minus x sine x.
Okay, so the pattern that you're going with is that on these on the left, the number in front keeps going up by 1.
Yep.
We get negative, negative, positive, positive. So the next one would be negative, negative, positive, positive. I think that's what you're going for.
Yeah.
And then
that's what
here,
it's
these
looking
keep
like.
switching. X sine x, x cosine x, x sine x, x cosine x, x sine x. Next one should be x cosine x. And the signs are doing the same thing. Minus,
Yeah,
minus,
okay.
plus, plus, minus, minus, plus, plus. That looks like, I agree with that.
Would be a
pattern.
reasonable assumption.
It's a reasonable assumption that the next one would be, for the sixth, would be -6 sine x minus x cosine x. And then the next one would be 7 would be -7 cosine x plus x sine x. Do you all see the pattern that it looks like has been established? Everything in green is a guess, okay? The black and the red we've done by hand. The stuff in the green is our conjecture as to what we think is going on. minus minus plus plus minus minus plus plus minus minus plus plus minus minus plus plus, right? These are switching sine, cosine, sine, cosine, sine, cosine. So I think what I'll do is I'm going to do one more derivative. And after that, if it matches this line, I think we'll be happy. So my fifth derivative is the derivative of this. So that's going to be 4 cosine x plus 1 times cosine x plus negative sine x times x. Now notice I went through that real quick. Derivative of a constant times a function is the constant times the derivative of the function plus, so I didn't really need a parenthesis here, but then I did product rule here. Also, as was pointed out by Ethan, x cosine x is the original function, isn't it? And we know what its derivative looks like. It's cosine x minus x sine x. So we've already done that derivative earlier in the problem. So this becomes 4 cosine x plus cosine x minus x sine x. And so we get at the end 5 cosine x minus x sine x. And does that match? Yes.
Hell yeah.
So we have a pattern, right? We have a pattern. But that doesn't give us the 28th derivative yet. It just establishes the pattern. So now we have to play that mod game, and we have to be careful because we got a lot of stuff going on here. All right. So how do y'all feel? Does this feel crazy or? I know some
I'm
of
not
y'all
gonna
are-
lie,
I know
the
some of
the
y'all are-
pattern thing is kind of messing with my head, but I can hash that out later.
All right, so let's imagine down this table, way down to the 28th derivative. Would you all agree with this? 28 is going to be there, right? First derivative 1, second derivative 2, third derivative 3, 4, 5, 6, 7, right? We should have that, right?
Yeah.
Now let's talk about, first let's talk about the sign in front, whether or not it should be positive or negative. Let's do that first. So let's take a look at the negatives. Negative, 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 negative. Let's just look at those. Those happen at 2 and 3, right? And they happen at 6 and 7. 2 and 3, they happen at 6 and 7. Where else would it happen? What would be the next one? Next group where it would be negative.
10 and 11.
So 8 and 9 would be positive. 10 and 11 would be the next group. Does that make sense? This is where we're getting a negative out front.
Yep.
That means that it's positive when we're talking about the 0 and first derivative, the 4th and 5th derivative, the 8th and 9th derivative, right? Then we're getting a positive out front. Let's think mod. Let's think mod. What should we mod these with?
I mean, it looks like our sine and cosine is looping on every 4 effectively. Say that 5 is if you're not looking at the constant, 5 is giving you the same as 1.
I'm not following you there.
The trig functions, ignoring the constant, that 5th derivative is the same as the 1st derivative.
Oh, I see what you're saying. If you ignore the 5, this cosine, cosine, this x sine x minus minus is the same. So maybe mod 4.
Yeah, I think mod.
But let's see, if we did these mod 4, what would, let's do this mod 4. Let's, what would this mod 4 be? What was 6 mod 4 be? 2, right?
2, yeah.
What would 7 mod 4 be?
3.
3, okay. What's 10 mod 4?
2 again.
2. What's 11 mod 4?
3.
3. And then if you do 2 and 3 mod 4, you're going to get 2 and 3. So it looks like if you're in this list, when you mod it, you either get 2 or 3, right? But what about this list? If we take 4 mod 4, what do we get?
0.
0, no remainder. If we do 5 mod 4, we get 1. Same with 8 and 9. If we mod those 4, we're going to get either 0 or 1. So what I'm getting at is if you take whatever derivative you're looking at and mod it with 4, if we get a 2 or a 3 out, we're going to have a negative in front. If we get a 0 or a 1 out, we should have a positive in front. We are doing the 28th derivative, right? So what would 28 mod 4 be?
0. 28 divides
Goes
evenly.
7 times, right?
Yeah.
So nothing, no remainder, which means it should be like these guys, right? Which means this should be a plus in front. Now, what about this part? Cosine, sine, cosine, sine, cosine, sine. Those keep switching, right? Switch, 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 right? So every time it's even, it's sine, right? Every time it's even, it's sine. Y'all see that? So 28 is even. So I should expect to see a sine here. Sine x.
There shouldn't be any even sine x's that don't have a positive cosine after it.
Mm-hmm. So what about this? We go minus, minus, plus, plus, minus, minus, plus, plus, but it's not the same as a number in front, is it? So if I take a look at this number, when do I get minuses? When do I get pluses? I get minuses whenever you're at 1 or 2. Where else?
5 and
5 and
6,
6.
9 and
And we
10.
get pluses. Yeah, pluses would happen at 3 and 4, and 7 and 10, or 7 and 8, right? What are the mods on this? What do the mod 4s give you on these numbers?
1 and 2.
You'll have a remainder of either 1 or 2, right? 1 or 2. And if you do mod 4 on these, you're going to get
3 or 4.
what do you get?
3 or 4. 3 or 0. 0. not 4.
0 or
3.
3.
Brain fart just there.
So what is 28 mod 4 give us? We already said was 0, right?
Yeah.
So we're going to be in this list right here. Because these are your mod zeros, which means that you're going to have a plus here. They all have an X, right? They all have an X. And now it switches again, sine, cosine, sine, cosine, sine, cosine, but this time the evens have cosines. And so I should expect this to be cosine. If your brain hurts, I get it. There's a lot going on there.
Yeah, this feels more out of like more difficult than even the discontinuity thing.
Is it? Yeah. Establishing patterns like that, understanding things like that is difficult. The only reason I'm doing it here is because I really want to kind of get you to at least see that a little bit. Because in Cal 2, chapter 8, it's called sequences and series. That chapter just destroys people because of this sort of like pattern recognition thing. It's like if you've never even tried it or seen this sort of thing, like you get to chapter 8 and it's all of a sudden you just hit this wall. So I'm just trying to expose you to a little bit of it. That way it won't be like brand new if you go to Cal 2. Not everyone here needs Cal 2, but most of you do.
Will there be anything like this on the homework of the ones like this, not just the modulus? Because there was some other modulus, but it was like the simpler one.
Yeah, this problem I took from the book, directly from the book, except that they asked you for, I asked you for, where was it? I gave you this x cosine x and I asked you for the 28th derivative. In the book, they give you x sine x and they ask you for the 35th derivative. So I'm not just like throwing some hard stuff at you just because I feel like, man, this is like a textbook. The textbook believes that at this point, you should be able to figure this out with what you know. So, yeah, that's why I don't want to send you to your homework without showing you something like it, right? All right, how are we doing? We got about 20 minutes. So you're going to need to practice, obviously, you're going to need to practice this homework 2-4. There's a lot to do there, right? But you just have the product of the quotient rule. That's all this section is about, right? So make sure you do your homework, ask questions, come for help if you need, tutoring or whatever. Watch my solution videos, whatever you need, but do not leave, do not proceed without feeling comfortable with this. And like, we are truly at a point where if you are struggling with this, it's going to be almost impossible to continue in the class if you can't do product rule and quotient rule and all the other rules, power rule, all that. Okay, I have some time still, and we could continue doing practice, trying to decide where are we in terms of our schedule. I'm trying to decide right now between more practice. We're behind, right? We're way behind. Yeah, we're still back in September on our calendar. All right, we're gonna have to move this train, keep moving it. All right. The good news is that the next rule is the last rule. Okay, so that's the good news. It's the last rule that we learn. And in calculus, after this, and pretty much from here on out, there are no more rules for taking derivatives. After this rule, in theory, you should be able to take the derivative of just about anything. All right, and it is called the chain rule. And now we are officially into 2.5. And so with the chain rule, just like with the quotient rule, product rule, you have to see it used a couple of times before you start to get a feel for it. All right. So if it seems foreign at the beginning, like what's going on, just give it a little bit of time. Okay. Hopefully you'll start to see what's happening. All right. So I'm going to start by giving you a function. And we're going to look at it and we're going to realize that what we've learned up to this point, we don't have a way of dealing with this, with what I'm about to show you. So let's say we take the function f of x equals sine, and inside the sine, I want you to put x squared. So when we look at this, and we're asked to find y prime, sorry, or find f prime in this case. When we look at that, we should notice that this is not a product rule, right? This is not a product, because then you're telling me that the first thing is sin by itself. What's sin by itself? Nothing, right? That's nothing. This is not a product. That's not multiplication. This is actually what we refer to in algebra as composition. This is a function that lives within another function, right? This x squared is buried within the sine function. That's, this right here would be a product, right? If I had x squared times sine x, yes, that is a product. I agree with you. But that's not what we have. We have the x squared living inside the sine. Y'all see the difference between a product and this? So naturally the question becomes, what is the derivative of this, right? How do we take the derivative of this? It's not a product. It's not a quotient. It's not even power rule, because you might be sitting here saying, oh, I take the derivative of this, that's 2x. I agree, derivative of x squared is 2x if x squared is by itself, but it's not by itself. It lives inside this other function, right? So we need a rule to be able to handle this. So what I'm going to do right now is I'm going to go to our good old graphing, our friend here. I'm going to graph sine of x squared. There it is. That's what it looks like. Okay, that's sine of x squared. And we would like to be able to figure out what its derivative is. And when we finish this problem, when I graph it, we should be able to do that thing where you look at the slope of tangent line and just like you did on your test, you should be able to look at a function, see what its derivative looks like, say, yeah, that's its derivative. All right, so how do we do this, right? How do we do this? Well, what we have to look at here is, again, first, the idea that this is composition, right? That we have an inner function and that we have an outer function, right? Like an onion, okay? Like an onion, there's an outer layer and there's an inner layer. Agreed? Another way you can kind of think about it to figure out what's the inner and outer is if I asked you to plug in x right now, if I told you right now, replace x with 2, what would be the first thing you do?
Square 2.
Square it, right? So that first thing you do is always the inner part. After you do the squaring of 2 to get 4, then you would take sine of 4, right? So that would be the last thing you do. So the outer layer is the last thing you do. The inner layer is the first thing you do if you plug in x, a value for x. All right. So how do we do this? Here's what some people might think. This is not right, but here's something you might think it is. You might say, oh, well, I know the derivative of sine is cosine. And I know the derivative of x squared is 2x. That seems like a plausible idea, right? Like, okay, yeah, sure. You took the derivative of the outer layer, you got cosine. You took derivative of the inner layer, got 2x. And I mean, that seems reasonable to me. Let's check and see if it is. Let's see if that is the derivative. We should be able to tell right away when we graph it. Is cosine of 2x the derivative? Can you tell?
Yeah, that's not even kind of the derivative.
What I would do is go to the purple one, right? And look at the purple one and look where it has flat tangent lines. Anywhere the purple one has flat tangent lines, what should we expect to see on the black function?
X-intercepts.
X-intercepts. And if you go down here, nope, no x-intercept there. Yeah, that's definitely not, no x-intercept here. No x-intercept. Yeah, that's not right. Can't be it, right? It can't be it. So we're going to have to still do some work then if that's not it. So I still haven't given you the chain rule, but I'm telling you that's not it, okay? It's not a product rule and it's not this. So what is it? Well, I'm going to show it to you first before I give you the rule. Here's what the derivative is. The derivative is, and I'm going to talk through it first. What I'm going to do is I'm going to take the derivative of the outer function first. What's the derivative of the outer function?
Cosine.
Cosine, right? Derivative of sine is cosine. So I'm going to write down cosine. But inside of it, I'm not going to take the derivative of the inner part. I'm just going to leave the inner part alone. I'm not going to touch it, okay? So it's like it's an onion. And so the first thing you have to do is you have to differentiate the outer layer of the onion, leaving the inside of the onion alone. Once you do that first step, then the outer layer is complete. And now you can move into the next layer. The next layer inside that is the x squared, right? Now you're going to differentiate that. What's the derivative of x squared?
2x.
2x. You will multiply it times the derivative of the inner layer.
Oh.
So look, it'll be this. This is the outer, derivative of the outer layer with the inner left alone. And then this, you multiply, I have to say that, then you multiply by the derivative of the inner layer. And you're done. That's it. That's the derivative. I'll give you a second to write that. I'm going to graph it now and we'll confirm that this is it. So all I need to do here is change that. I needed to take the derivative of the outer layer, which turned it into cosine, leave the x squared alone, and then multiply that times 2x. And now let me back out here a little bit. If we look now at everywhere the purple one has a flat tangent line, we'll go down and we will see an x-intercept of the black graph. Purple slope tangent line is 0, come down, boom. Here, slope tangent line is flat, x-intercept. If you look just between here and here, the purple function is going down, which means we should expect the derivative to be below the x-axis. It is. Okay, I'm just trying to convince you visually that that is it.
Can you zoom up out a touch?
Say again?
Can you zoom out a touch? I want to see what it's doing on its ends.
Yeah, I need to. It's just going to get crazy.
Oh, Lord.
Yeah, it's just going to get crazy.
Scary.
Cool graph. All right, let's try another one. All right, let's try another one. I still have not given you the formal rule. Okay, I'm going to wait, I think, till next class to give you the formal chain rule. I want you to think about it like an onion right now. Okay, here we go. So let's say we have f of x equals x to the 4th plus 4x cubed plus 1 raised to the 747th power. So if I had told you, if I had put that down and put like all of that to the 2nd power, you might be tempted to actually like FOIL it out, like multiply it all out and then just do it term by term. By me putting 747 there, I'm making you submit. And basically you're not going to want to do that, right? So is there a way to do this, right? Can we do this? So is this a function living inside of a bigger function? That's what you have to see here. You'll see.
Would it be the x to the 4th plus that whole thing is the one function, and then the whatever's in there to the power of 747 is the other?
Yeah, you have basically everything in yellow is like the inner layer, right? The inner layer. And if you plugged x in, you could figure out what the yellow part is, right? Once you figure out the yellow part, then you go ahead and do the next layer out, which is the raise it to the 747th power, right? Y'all understand that? This is like the outer, and this is like the inner.
So what is the chain rule?
I'm going to give it to you next class.
Are you always going to do the outer first?
You always do the outer first. Okay, so I wrote it down in words. This is what we're going to do every time we use a chain rule. You identify an outer function and an inner function. You take the derivative of the outer function and you do not do anything to the inside function. And then you multiply that times the derivative of the inner function. Let's try it. So the outer function.
We just take that 747 out front and then subtract 1 from it and then leave everything alone on the inside, right?
So if the outer function is basically the green, what it is like, it's almost like x to the n, isn't it? It's almost like x raised to the 747th power, right? If I asked you to take the derivative of x raised to the 747th power, you would bring 747 down, and then you would take that x, right, and raise it to the 746th power, wouldn't you? But see, the thing that's inside is not x. The inner layer is all that stuff in yellow. So we want to put that in here and not touch it. Just leave it alone. Don't mess with it. Okay. Then you multiply, because in chain rule, you always multiply. And now you're allowed to go look at the inner layer. So it's kind of like you've peeled the outside layer off. You've already differentiated it. Now you're looking at the inner layer, which is the part in yellow. Take its derivative now. So what would you get?
4x to the 3rd plus 12x to the 2nd.
Plus 12x to the 2nd. And then the derivative of 1 is 0, right? One more thing. parenthesis. You have to have the parenthesis there because you're multiplying. If you don't have the parenthesis here, right? If you don't put parentheses here, the only thing you're multiplying is this 4x cubed times this. You need the parenthesis because it's all of it times this. Now, I'm not going to graph this one because the computer will not be able to handle this graph, but that is the derivative.
Exponent's too big for it.
It's too big. Yeah, I think it would freak out.
I would like to see that.
You want to try it? We can.
Yeah,
I think
just plug it
would
in.
freak
Let's
out.
see what it does.
X to the 4 plus 4x cubed. X to the 4th plus 4x cubed plus 1. Let's raise that to the, hello. Raise that to the 747. Actually, didn't do too bad there. Except that, I mean, it just becomes so big that it almost looks like a vertical line. Yeah. Yeah.
What?
It's
So-
a weird function.
What would this function actually look like if it wasn't like if you drop that exponent down, would it still be the same general shape of a function if you just made a smaller number? Like,
We can
with
make
the
it n,
square.
and then we can let n vary. We can let n vary and then look at what happens.
Yeah.
So like if it's just to the first power, that's a polynomial function, right? If I just start
Oh,
raising power up, these are all polynomials. Because you could theoretically expand that out, multiply it times itself 747 times. So it is a polynomial function.
Okay. So it's basically a glorified parabola. It's kind of what it was looking like.
In some sense, yeah.
It just was really freaking weird.
Yeah. Mhm. This was really just to illustrate how, yes, I can make that a smaller number, but then you might try and get around the chain rule. So here I force you to do chain rule. Okay, let's do another one. You ready? F of x equals, let's go with tangent of x sine x. Tangent of x sine x. The x sine x lives inside that tangent, right? The way I wrote that, I'm doing tangent and then inside x times sine x. Oh yeah, now we're talking. There's the graph.
What the heck?
Yeah. Okay. Now, I'd like to know the derivative of this. Let's take a look at the inside layer. Do you see the inside layer here? That lives
that's
in
gonna
the
be-
tangent, right? That's inside the tangent. That's the inside. Here's the outside. So our outer is here. Our inner is here. According to what I've told you so far, and again, I haven't given you a formal rule, what you'll do is you'll start by looking at the outer function. You'll take its derivative, right? And then you won't change this. So what is the derivative of tangent?
That's
Secant squared x.
Secant
Secant
squared.
squared x, right? Secant squared, but see, I'm not going to put x in here. What am I going to put in here?
The x sine x.
The x sine x, the inner function unchanged. That's a critical thing to understand. We're taking the derivative of tangent of a yellow box. The derivative of the tangent of a yellow box should be secant squared of the yellow box, untouched, right? Untouched. Then we come in and say, now the next link in the chain is the derivative of the inner function. And when you look at the derivative of the inner, you say to yourself,
F.
We have x cosine x.
that's what?
Sine x plus x cosine x.
It's a product rule. Do you
Oh,
see
there you
that? It's a product rule. See, these are all going to be intertwined now. Like you have to be so careful on what we're looking at. So we took derivative of the outer, which is secant squared of the inner function untouched, times now the derivative of this. That's a product rule on that. And that will be 1 times sine x plus cosine x times x. Product rule for that piece. So it's secant squared of x sine x times sine x plus x cosine x. That's our derivative.
One thing I'm seeing is there may be some we encounter where it may be easier to use our limit definition to find them.
I don't know.
Well, there was that one earlier where we had to use the quotient rule and the product rule.
Yeah, I still don't think the limit would have been. Yeah, I mean, the limit is almost never better. Because the algebra is tricky.
Yeah, that's true. Yeah.
All right, so we're almost out of time. I want to just show you one more. Okay, one more. I don't want you doing any homework for chain rule tonight. Or this week. I want you to just focus on product and quotient. Make sure you understand that. All right. But here's one more. F of x equals sine. Inside the sign, I want you to put sine, and inside of that sign, I want you to put sine of x. So this is a triple composition. You have a function inside of a function inside of a function, right? Sine of x is a function. If I told you to plug in x is 2, you would figure out what this is, right? You do sine of 2. And then after you get sine of 2, you'd plug that into sine again. And you get sine of whatever that is. And then once you figure that out, you do sine again, wouldn't you? So this is an onion with 3 layers. An onion with 3 layers. How do you think we take the derivative of an onion with 3 layers?
Same way we take with an onion of 2, just extra time.
Outer layer, right? You take the derivative of the outer layer, you leave the inner layers, both of them alone. Then you move into the next layer, take its derivative, leave that inner layer alone, and then move into the final inner layer. So let me see, I'm almost out of time. So I'm just going to show you what this answer is. And we will look, if you don't understand this right now, I will take smaller steps next class. All right. I will present it in a more formal way. So my outer layer is sine. Outer layer, middle layer, inner layer. Okay. Out, middle, inner. Start with the outer layer. Derivative of the outer layer is cosine. Cosine of what? Well, the other layers inside of it unchanged. Times, I've done the outer layer. Now I'm moving to the middle layer. The middle layer is sine. What's derivative of sine? Cosine. Cosine of what? That inner layer untouched. Done with that layer. Move in, times. Now I'm ready for the derivative of the inner layer. Cosine x. There, that's my derivative. So if, you know, the thing about the chain rule is this. If you can grasp it in an abstract way without me giving you the definition, it's better for you. If you have to go through the formula version of it, I think the formula version of it will be easier for you, but it will slow you down in the long run. You eventually want to get to a point where you can just like do what I just did, but that'll take some time. Okay, so it's 240. Quotient rule is the main thing. We'll come back and do chain rule. I'll introduce it formally like you've never seen it before, and we go from there. All right.
All right.
We're going to be taking the third derivative of this answer, or like the fourth derivative of this.
Oh yeah, can you imagine what the if you were asked for f double prime of this that would be a nightmare, because you would have a triple product, right? So you have product rules there. So you would have to do like maybe group these together and do this as a product rule first. So you do derivative of this times this plus derivative of this times this. And when you do derivative of this, that's a chain rule. When you do a derivative in here, it's a product rule. Yeah, we're talking real bad. So I wouldn't, that's not going to happen to you. Okay. I'm not going to give you, I would never give you something like that. But theoretically, it could be done. We have all the rules we need to do it.
That would be a nasty problem.
Yeah. Yeah.
I think I know why you use the onion metaphor,
Yeah.
because onions make you want to cry when you peel them, and
They
this
make you
makes you
wanna
want to cry
cry.
as well.
Exactly. Exactly. Look, the chain rule is, you know, it's kind of the make or break part of calculus 1 and differentiation. But y'all can do it. You just, it's like a little switch. I will say that one of the things that really prevents people from doing well with it is just that these little algebra things like this, and like I tried to show you in the very first problem. I'll put this there, and the student will say, okay, the derivative of that is cosine x times x squared plus 2x times sine x, or sorry, yeah, sine x. Okay, that's not what this is. This is not a product, right? You do not take, I see what a student did here, right? They looked at sine, they said, oh, derivative of sine is cosine. No, derivative of sine of x is cosine x. But sine, S-I-N, those three letters by themselves have no meaning, right? So this makes no sense. Those are the little things that it's like students are uncomfortable with notation. And so they get really hung up with the chain rule and product rule, quotient rule. Yeah, practice. I'm trying to teach my daughter right now how to solve linear equations, right? She's in 7th grade. They're solving linear equations. And it's like, you know, I don't force math on her. It's like, if she likes it, she likes it. But she's doing really good. And I'm like, you know, when we first started, it was like she was having trouble with sine numbers, right? -7 minus 2, right? -7 minus 2, -9, right? So in the beginning, she was having trouble with that. I said, just repetition. Now she can do sine numbers in her head, no problem, you know? And it's like, I was telling her last night, I was like, repetition. You've got to do it. You've got to do it. And you get to this level where you get comfortable with it. And with all these rules, that's a big thing. I know, Daniel, you asked a couple of classes ago about practice. I'm very sure that if you got onto Google and just did like worksheet on chain rule or worksheet on product rule or worksheet on quotient rule, you would find very useful stuff there. Very useful, because the rule is the rule, right? So you probably start with problems. They give you problems that start out real simple and then get harder and harder. So practice. And you'll get to a point. I mean, you will get to a point where you feel like, yeah, give me anything, I'm good. You know, like I feel good about it. You can't give me anything, it's gonna intimidate me. You know what I'm saying? Like you'll just get to a confidence level with it. But you gotta practice. All right, everyone.
All right, thank you,
Great
sir.
weekends. Yep. Have a great weekend.
You too.
Thank you, you too.
Bye, have a good weekend, sir.
You as well.
Okay.
Appreciate it.